Howdy students. Let's talk about element 4 under section D of the Physics C curriculum of E&M, and that section D is magnetic fields, or magnetism actually. Where's it, magnetic fields? Well, element D I know is Biot-Savart's law, and we'll get to that in a minute. There are two expressions that we can use to talk about fields made by a point charge. And those fields can either be electric or magnetic. Now, for sure, this charge Q creates a field at point P, and that field can be expressed as 1 over 4 pi epsilon naught Q over R squared in the R hat direction. Here is a vector R that locates point P relative to our charge, and the R hat direction therefore is in the direction of this vector R. So this electric field here looks like this. Generally, sure, fine. Okay. Now, yes, end of story, that is true. The charge is there, point P is there, the field looks like that. If this charge is currently moving, there might be a magnetic field at point P. Let's say the charge has a velocity v that looks like that. Well, in this case, there will be a magnetic field at point P, and the strength of that field we can write in a way that's very analogous to the way we write, I should do this, the way we write the strength and direction of that electric field. And it looks like this. We say that there's a magnetic field B that is, well, we do get a 4 pi. We don't get a over a epsilon naught. We get a mu naught over. And here's the deal. There can't be a magnetic field if charge Q isn't moving. All right? As we talked about in some introductory stuff, the nature of all magnetic field is from moving charge. All right? The fact that this charge moves means there might be a field at point P, and there is a field at point P as long as this expression can evaluate V cross R hat over or R squared. Q, there's a Q in there. There we go. So as long as that cross product can evaluate to a non-zero, then there is a magnetic field at location P. All right, now the direction of this is going to follow via this part a right-hand rule. All right, so our R hat direction looks like that. If we do V, vector V cross R hat, I'm putting my fingers of my right hand in this direction. I'm curling them toward R hat, right? And then my thumb is going to point in direction of magnetic field, and I can point my fingers in direction of V and curl them toward R hat. So that means that magnetic field at this location, fingers to V, curl towards R hat, thumb then points into the page, and that's my X to mean magnetic field B here points into the page at location P, and it has that magnitude. Well, that magnitude, I should say that. This magnitude evaluates to mu naught Q over 4 pi. Well, V cross R hat is really V times R hat perpendicular. All right, so in that case, there's a V. You could do a V perpendicular to R hat. All right, that would be a V perp. So we could say perhaps V perp. Well, this stuff really is this. It's magnitude of V perp times magnitude of R hat. Well, the magnitude of R hat is 1, so we don't even include anything with R hat. So then we can say over R squared. I'll put that perp back there. All right, and this is, in this case, going to be, I'm not going to write that. The direction has to follow right-hand rule. We'll just state that. Okay, So this just says that, I mean, the bottom line is, as long as, this part says, as long as there's a component of velocity perpendicular to vector r, and in particular, perpendicular to the r hat direction, then there is a magnetic field at point P. So the only time we're not going to get a magnetic field at point P due to the movement of charge is if the charge was, say, here and moving that way. All right, a charge moving that way creates no magnetic field along the line of its motion. It creates a field everywhere else. So everywhere out here, everywhere out here, everywhere, I mean, from this charge at this location, here, there is a field, right? Here's the line of, the direction along which this new charge is moving. And so everywhere along that line, there is some magnetic field. All right. Now, more typically, so what I want you to notice, I should say, is I want you to notice the analogous nature of these two expressions. All right, they both have this over 4 pi thing. In our electric field thing, we get the electric permittivity of free space, or vacuum permittivity. Here we get the magnetic permeability of free space. Yeah, and it certainly depends on how much charge. We get a r squared dependence. All right. Here, the simple presence of charge means there's a field everywhere in space around it. Here, we have to meet this requirement where the cross product V cross r hat has to evaluate to non-zero, which means, like we said, everywhere except for along the line of motion of the charge, there is some magnetic field. Okay, so those expressions are very analogous. What we will more typically do, however, is we won't necessarily as often talk about a magnetic field made by point charge. We'll talk about this wire carrying a current I, and we'll talk about the field at some location due to the current in that wire. And so what we'll say is, here's a little, this here is a little dl, and in particular, dl is a vector, goes that way. And so we can say, well, from that little current element, right, I call this IDL a current element. Well, look, here's a vector R that locates point P relative to our current element. And this is sort of like saying, okay, we can say that there's a little tiny field made by, let's see, mu naught over 4 pi, and then we get Q V cross r hat over r squared. That's for a point charge. And now what we can do is say, well, V dB mu naught over 4 pi Q V we can write as dl dt. I'll keep the cross r hat over r squared. And then looky here. Oh, now, how much charge? This is not a point charge. This is a tiny little amount of charge, dq. What's a tiny little amount of charge? This. In here, there is a tiny amount of charge, dq. And that dq dt, the rate at which charge moves, is current. So this we can write as mu naught over 4 pi I dl cross r hat over r squared. And this is really a vector equation, so I can do that, because the right-hand rule nature of this cross product is going to yield the direction of this dB vector. All right, and then that is Biot-Savart. That's Biot-Savart's rule, is that the magnetic field at some location from a current, well, I'm just going to write it over. That's a pi. I dl cross r hat over r squared. Integral You can integrate the whole thing. The I is probably going to be constant, so that can be probably pulled out. Um, so where we put that integral sign isn't the most important, but that's Biot-Savart's rule. All right, so again, very analogous to Coulomb's law in that it allows us to find the field made by any current at any location. Let's talk through a couple of examples. Here is a loop of current somehow. I don't know what's making this current flow, but there it is. Current's coming out here. It's going in here. It's down the front, up the back. And we want to know what the field is there at center of current. All right, so I'm going to take a little element of current here, and that's coming toward us. So I'm going to say that the magnetic field is the superposition of all the little magnetic field elements. All right, and let's see. We'd use right-hand rule to say, for this one, what I would do is I would put, well, how about this? From that one, we get a R vector that goes that way. From this green current element, we get a R vector like that. All right, and then so from that one, if we do that little dB vector is going to be mu naught I over 4 pi dl cross r hat over r squared. Now this cross product, let's see, we go fingers in the direction of dl, and that's out of the page, and then toward r, curl my fingers toward r, my thumb points to the right, so the dB from the top points that way. Yeah? It's okay? It's okay. And let's see. From the bottom, I'll do this one in red. We get a DL, an IDL, if you want to call it here, that's going into the page with an R vector like that. So fingers in, curl towards R, and yeah, this dB points to the right. And they all do. No matter where we do this, if you take one here in the front, that current IDL would be this way, R would be into the page, and then yep, that points right to. And that follows a different right-hand rule that we talked about, that if you want, you can wrap your fingers in the direction of the current, and your thumb will point in the direction of the field inside the loop. So this follows that. All right, so we can now say that the field from this is the integral of all those. So B, let's see, mu naught's constant, I's constant, 4 and pi, oh, and R's constant. This R is the spatial radius of this hoop that we should probably call big R. So this thing is mu naught I over 4 pi. I'm going to take this and make it big R squared. DL cross R hat is, well, every DL and R hat are perpendicular. So this integrates to, sorry, this cross product evaluates to the magnitude DL times the magnitude R hat times the sine of the angle between them, which is 90. So it's that that scalar product, and the magnitude of R hat is 1. So this is DL. All right. So all we're left with is that. Notice this is dB. We're integrating that to get the total field. And the only thing that varies, the only thing we're left with is to integrate dl. And so that's the length L of the loop itself, mu naught I over 4 pi R squared 2 pi R. And then this goes with that, and this goes with this, and this we're left with a 2. And we get B is mu naught I over 2R. That's the magnitude of the field right? We want to make this a scalar. Sorry, we want to make this a vector. We say via our right-hand rule, the field points that way at center of hoop. What say you? I say good. Okay? Yeah, right. Let's say slightly more complicated. Let's go somewhere out here. Let's call it a distance x from that hoop. All right, we got the same current going down the front, up the back, out here, in here. All right, we want to talk about field at that location. This gets a little weird. Now, I'm going to do the same two DLs or IDLs. I'll do my green one up top. This IDL coming out of the page. Here's a vector R that locates it. All right. That IDL's out of the page. So from that one, right, that DB there, vector-wise, is going to blah, 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 mu naught I over 4 pi DL cross R hat. So what I'm concerned with is this part, because we got to get that step one down where we say, what do I actually have to integrate to get the whole field? DL cross R hat. DL out of the page, R hat like that. So DL out, R hat like that. This field here points this way. Okay? Again, you take your DL out of the page, cross R hat. This is the R hat direction, same as the direction of vector R. All right, so fingers out of the page, curl fingers toward R hat, and your thumb points perpendicular to R. If we do another element down here, let's do it in red, and here's the R hat direction for that, right, because here's the whole vector R. So out of the page for DL cross R hat, oh sorry, not out of the page, into the page for our IDL, and cross R hat, and we get a field that looks like this, dB, again, perpendicular to that vector R. All right, so what that says is, symmetry says the vertical components of these two fields add to nothing, and we will add up all. So while vector B is the integral of all the dB vectors, that's going to evaluate to dB x direction. Right, here are dBx, dBx. Okay, so if we were to call this an angle theta, let's say, then that angle theta is here and or here. So that's going to be dB sine theta. Okay? Now, how are we going to write our dB? So, net B is going to be dB. dB is mu naught over 4 pi IDL cross R hat over R squared. Now I got to keep this sine theta. Right? And I've got to integrate, and I can put my integral there. I can put it wherever I want, but that's the appropriate place to put it. All right? So now, what varies here? Well, I's constant. The magnitude of R is always the same thing. Theta is always the same thing. So you got to imagine this this thing is kind of like, you know, like this conical deal here, where no matter where you are on here, that's supposed to be dotted, the angle between that central axis and whatever part of the cone is always the same angle. Does that help at all? It's the same angle. Theta does not vary. So let's see, that means now our IDLs and R hats, or our DLs and R hats, are still always perpendicular. All right, out of the page and this direction are perpendicular. Just because this doesn't point that way doesn't mean that out of the page isn't perpendicular to that. It still is. Okay, so this B is mu naught I. I can keep the sine theta. The r squared, okay, that r squared is, if we say this has a radius r, that r squared is r squared plus x squared, right? And all we have to integrate is dl again. So B is mu naught I. Well, sine theta. Let's hang on to that for a minute. Sine theta. Well, sine theta is going to be r, big R over little r. So let me do that. Big R over little r, r squared plus x squared. Integral dl is that. Yeah? And, well, this r is square root of r squared over or plus x squared. So here we're going to get one of those things you might recall. So this gives us a I don't know, how about a 2 pi mu naught I r squared over r squared plus x squared to the 3 halves. How's that feel? And that's going to be, in our case, in the that way direction, whatever we call that. It's okay? Fair enough? Now, of course, if you're really picky, then you'll want to have followed the rules of algebra and kept that 4 pi in there and all the way down to here. You know, picky, I guess. You know, if you want to be like that, you could do it correctly algebraically, I suppose. And then we got a 2. Still a mu naught. Okay? Fair enough? So, this gives us an introduction to using Biot-Savart's rule to find magnetic field made by either a moving charge, a single moving charge, or a current carrier made of lots of little charges. All right, it's way more common to do, the actual IDL cross R hat form. I mean, that's really is Biot-Savart's law. This, point charge thing allows us to get there by turning our QV into an IDL. But one thing, this is the same as some of my dudes get in trouble with, is being able to do this part is perhaps the most important physics part of the whole thing. All right, so the people that get in trouble say, well, B is the integral dB, and dB is mu naught I over 4 pi dl over cross r hat over r squared, and they forget about, oh, well, there's this nature of the field like this and the field like this, such that these are the only components I have to add, and being able to turn this, add up all the vectors into how do I actually analytically evaluate the magnitudes of stuff I'm adding up. That's a good physics part. All right. From there, it's kind of plug and chug. The rest is some calculus. That's not trivial, but I mean here it's pretty trivial. In some cases it will be less so, but get that part in the box down. All right, where you figure out before you start jamming big equations in there, what is it I'm actually adding up. Okay. All right, folks. More soon. Farewell.